I asked him to do this session, and then a number of other people asked him to do other bits as well, but I got him first. Gnuradio for me is certainly a sort of black art. And when he, a couple of months ago, said, "Oh, Gnuradio's easy," I said, "Well, tell us how easy."
Graham's completely calling me out on that one, I think. Yeah, so I'm just going to kind of get a bit of a feel for the room. Those of you that have used Gnuradio before? Okay, about half of the room. Those of you that feel like they're proficient in Gnuradio? Okay. So for those of you that you just had your hand up last, this may be slightly, what's the word I'm looking for? Rudimentary. But for those of you, the half of the room that actually hasn't heard of it or played with it before, this is really just to give you a feel and an understanding of what this tool can do for you when you start using software-defined radios that small little dongles that you can connect to much better front ends than what I've got here. And what are the things you can do to start manipulating the signals that you're actually getting? I do have to say that there's a lot of learning that obviously I've done myself, and obviously that's one of the things as an amateur and an academic you continually learn. And I've learned off other people, Brian Yeomans, Alex Sestayers, most of you will be familiar with, and Dania Estevez, and there's many, many more, not to mention everything that you will possibly be able to bring up via Google, on the forums, all of those things. And hopefully I've tried to collected a lot of these things down, and it's the sort of things that I also kind of teach about in my classes. So, as I am primarily a lecturer, we have presentation learning objectives, which include, hopefully, to get an investigation of kind of what the tools are. And it's mainly built around something that I'm going to talk about today, called Gnuradio Companion, which is a graphical user interface that allows you to kind of drag and drop elements into a panel, and you can simply connect them up by clicking on them. And really what we wanted to talk about as well is the understanding of what we do with regards to sources and sinks, the different data types that you have in the system, when to use them, and to really get an appreciation of something called rate matching, which is where as soon as you start putting samples in, say for instance the one that I've got here, which is can go up to 2.4 megasamples per second, you need to kind of match these things all the way throughout the chain, and understand that when you start using these things, if you're trying to hear something, and that's coming out of a PC speaker, that will be 48 kilohertz or 41 or 44.1 kilohertz. All of these things need to be matched. So you'll be interpolating, decimating, and just understanding what things are coming out when. More importantly than not, as soon as you start going digital towards things like TNCs, obviously those rates aren't going to be coming out as frequently. Typically, you'll be waiting for a certain thing, whether it be a sync vector, a word, or a 7E typically. You might be looking out for very, very particular things. And so what we'll be looking at is, again, some simple examples, just to give you, an understanding of exploration of the sort of things that I use it for. So, there is no coding necessary. You can actually get away with this by dragging and plopping blocks in, obviously that's the verb I would use, plopping, into the system as a whole. And it can be actually very, very easy. You can use this as quite crude and obviously quite dedicated test equipment, and they're dedicated around these sort of blocks that you can see here. And you're going to want to try and match up your sources with your endpoint sinks, and then you're going to want to manipulate all the different variables and variables that come with them. Okay. Again, these are all things that you have in your head that you typically just fiddle about with on an icon. So things like your center frequencies, how much correction you're going to be using, your gains of your system, these are all variables that you're all very much used to using, but instead of actually having them in physical pieces of hardware, you're just going to be clicking on blocks, opening them up, typing in your number. That's the real sort of one of the big powers of software-defined radios, is obviously that flexibility, and that's the sort of thing that we're looking to really exploit here. The same thing, again, goes around with your sinks. You can start plotting all sorts of weird and wonderful things. So when you wanted to change your frequency, obviously other than typically turning a wheel on an icon, you might be wanting to use a range. And so for instance, if I'm looking at a certain value or a certain range, you can just, again, drag in one of these range blocks there, tell it how far and how low you want to go, how much you want to scan yourself, and then start to define your problem of what you want your program to actually do. And when you run this sort of thing, it allows you to then bring in the samples from the software-defined radio. All of the device drivers in Gnuradio allow you to do that. There's all sorts of ones available, and they can go up to 56 megahertz of bandwidth in some of the new SDRs that I've been looking at and working with at the moment. And so they're hideously wideband. Okay, so if we're thinking of typically a 20 kilohertz channel, you need to think bigger. What else is out there and what can you do? And so these sort of simple tools you can pick up your pages with, APRS, S-band signals. I've even been doing it with a Bluetooth keyboard just to actually test the sort of things that you can get out of there. And so, hacking around what RF you can literally pick up. A typical one that you can go out and buy at the more expensive range are USRPs, and those go up to best part of 6 gig in a fairly reliable way. So there's lots there to explore as well. But these are the sort of main blocks, and you'll be sort of dragging them around the system. So Gnuradio itself is built around this GUI, and if we just sort of have a look at this one here, you've essentially got blocks that you've built. Okay, I can make sure that all these slides go up on a website, and I'll make sure we give them things. I'll use the red dot. And really, what you essentially have is you have, like most systems, you have a top sort of bar where you can then start to press, compile, play, add in blocks, and move blocks around. And you can then essentially use a search panel to then go and get a block from here, and you've got all of these different pieces. And so these are essentially DSP blocks that are written in C++ that are then compiled and hopefully optimized, okay, for running on your given system that you're using. Okay, 99% of these things will want to run on a Unix POSIX system. So that kind of rules out Windows to some extent, but Gnuradio will operate on Windows, albeit begrudgingly. So really, I mean, this sort of stuff is the sort of thing you can look at. And for those of you who can't see it, you've got audio blocks, channel models, error coding, funky dongles, modulators, NOAA systems, OFDB, OFDM. I'm using it to kind of reverse engineer a DVBS2 receiver, because there's really kind of no blocks out there for doing kind of all of those video things. It has all the transmitter blocks in the DVB things, but it doesn't have the other ones. And of course, people keep extending these things. So it kind of started out actually just to be a system very much similar to MATLAB's Simulink, where you can drag and drop sort of control blocks in and around a sort of panel. And when you actually click compile on it, what it does is it builds a Python wrapper that you can then use to instantiate all of these C++ software objects. Okay, still with me? Okay, we're good. Okay, there's one thing that I wanted to bring out and why I put this slide up, is if you start seeing these things down here, this is the kind of console output that you would typically have from a program. And if you start seeing U's and A's and U's and A's and U's and A's, okay, it means that you've been underflowing, okay, or you've been doing something wrong with your sample rates. So this would be where, for instance, if something wasn't matched properly, okay, in your system, you're going to have a bit of trouble. So this is where, okay, I want to go into sort of more of a demo sort of phase. Obviously, this is where it could all go wrong, so please bear with me. Looking a bit further closer at that particular block, we can go through just a very simple FM receiver. We've got our RTL source on one side, and we pass it then through a low-pass filter to actually take out what we want. And then there's a magic block in there, which is just called wideband FM receive. And it will convert, okay, your actual INQ data, your complex signal, into then a floating point output. Okay, this is where these colors kind of come into play. So these blue ones that you see coming out of these blocks, this means that you've got a complex signal. It's an RF signal that's going to be coming out. And as soon as you see these orange blocks, it means it's a float. Okay, so the data types and the rates of those data types are going to be important. So if you're going to be writing your own blocks to do these things, you're going to need to be managing this whole chain. So let's just kind of start from this particular system, an RTL dongle, on this side. I'm sampling at 2 meg, and eventually, if I want to hear some FM, I've got to come all the way right down to what my speaker's going to be outputting. Okay? In our case, I think I'm using 44.1 kilohertz. So I can pass it through a low-pass filter, and I can then already, at these points, start to decimate my data. And decimation is essentially, if in this particular case, it's just throwing away bits. Okay? I don't want those samples, is all we're saying to that. And that becomes particularly important because as soon as you want to start decimating down and choosing what frequencies you want to cut off with, you can then pass them through there. And these rates have to match. So if we've gone from 2 meg divided by 4, we've now gone to 500 kilosamples per second. That's our quadrature rate, of which we would then want to analyze our FSK or our FM signal. After we've done that, we can then use a special block called a rational resampler, which is then what converts it to our 48 kilohertz. Okay, once we've got it down, we've actually divided it by 10 there. There's another audio decimator there. So 2 meg divided by 4, 500, divided that, gives me 50, and then I interpolate it back up, divide by 50, times by 48, to give me my 48 kilohertz audio output. And what I've then done is I've then just dragged a block over called AudioSync. All these libraries, they're all built there for you. It allows you to then go ahead and then drag in these things and use them. And I've used a couple of these range things just so that I can then play around with the menus. Here I've got my center frequency that I might want to be looking at. I want to then tell them how big a range that I want my filter to be. And then I've just got a volume switch which then multiplies and amplifies that signal. So let's go ahead and try that one, he says. This is what Gnuradio looks like. And when you hit this button here, it says Generate Flow Graph. When you hit that one, that will be generating our Python file. And then when you hit play, he says, everyone cross everything. You can start to then see what you've then got output. Now, let me turn up my volume.
We can do to reduce the pollution of those packaged items like drinks bottles and coffee cups.
You can see what I've been actually outputting is essentially drag and drops of all of these blocks together, and I've just happened to center it on an actual signal here. Now, if I didn't want to look at the audio coming out, I can just disable blocks. I can go in and go, yeah, I don't need to see that anymore, that looks good, let's just get rid of that. And so you've got these guys here, a sync, and I've got a time sync on there. Remember, any point you want to view something or have an output, you can put a sync. You can click play again. And then it will redo it all for you. So that looks like that's a little bit off. There's our signal. And we can look at it on a much wider display. So I can, at runtime, change my filter input. All of these tools, very, very powerful things that you can do with an SDR. Okay? To try and do that on an icon is obviously hideous. Taking these things apart, pulling out different components and adding different elements. I'll turn it down just a little, just so you can see it running. But this is the sort of thing as well where you can then get very crude waterfall displays, very crude time displays of what's coming out of your INQ. You can see there it's a bit quiet, but you can then have a look and analyse this signal. Once you've got it in the digital domain, it's yours. You can play with it. You've got functions that are there to help you manipulate these things. And the next question is really which DSP book do you want to then start to pick up so that you can, again, mess around with all of these different pieces. So to that sort of point, we can then go, okay, we've got a simple receiver, he says, and we can get some output. And you can use these nice sort of tools, you know, by dragging and dropping these blocks in to then actually then view your signals. So things that you would typically use SDR Sharp for, or GQRX, all of these things, you can make on your own. You can make your own WAV sync, you can make your own decoders. And that's kind of the next thing to kind of go on to. Again, the blocks start to begin to look a bit messier, okay? The ones that I'm going to show you today are not the ones that usually would go on my course. These are sort of ones that sort of get people into things that aren't as scary with some big scary blocks in them. And what we're doing is we're, again, bringing in sources, but in this particular case, I'm using a WAV file. So I can record something in SDR Sharp or GQRX, and then I can go back ahead and then play it back. I can then go in Audacity, cut out the bit that I know has got a signal in it, go back and play that over. Get that thing working in exactly the one way that I want it to work, because remember, you can play with all these variables. All of these variables in here, you can do at runtime. And when we start actually building up our very own TNC, you will then start to need to think about, well, how do you decide what is then a 0, what is then a 1? How do you define what those things are, whether it be tones, different types of signals? And when we pass our signal through, when we're in our baseband audio, we then start to look at, again, filtering it down. And these, again, are sitting on a slider, so I can change these things, the filter widths, etc. And then I want to then do something which is understanding how we can recover our clock. And the clock recovery is based on a Muller and Muller algorithm, which is based on a 1960s paper. And that 1960s paper essentially has been implemented in one fashion in Gnuradio. And what it essentially does is it tries to find the center of a given symbol, but it also does a whole bunch of other stuff in there at the same time as well. And this is kind of the problem when you start to use other people's libraries, other people's software. Because unfortunately, this Muller and Muller block, which is meant just to find the center of a symbol, actually also decimates, does a zero mean slicing, and has an FIR 8 tap filter inside it there. And of course, when you get that out of here, you're going to then get some sort of variable output. Because we're then starting to understand when noughts and ones exist, that's going to come in at whatever rate it thinks that it's detected. In our case, I then want to slice it. I want to then convert this float into noughts and ones, so we slice it into binary pieces. And then, I then want to descramble it. In this case, what I'm interested in is converting this system into a HDLC TNC operating at 9K6, in my case. Now, bonus points for those of you that had your hand up the second time. There is a block called a Descrambler, and it uses a mask of hex 21. Would anyone happen to know what that is related to? Sorry?
Square wave clock.
Square wave clock? Not quite, no. Mike, you reckon you know? What this Descrambler block would be, the mask? Why it would be 21 hex? Okay, which is based on what? There's a word that I'm looking for. It's G3RUH, which is based on what? Again, we have to come back to the raw mathematics there, which is, Kieran, you reckon you got it?
Yeah, I was just stretching.
Just stretching, all right, okay. It's actually based on the polynomials in which you're using for your scrambling. Okay, and so if you know what the polynomials are for a given scrambling type, a different demodulation type, a different whatever that you're using, okay, whatever standard it is, whether it's a CCSDS, a HDLC, all these different things, these are polynomials that match 1 plus your 12th and your 17th bit. Okay? And of course, though, you have to dig around for that. Because it just says, hey, there's a thing there, what's your mask that you want for your descrambler? And you're like, I don't know. But I'm telling you, that's kind of where it kind of comes from. After we've gone through that, you can then manipulate these things using, again, bytes to understand and not and add things together before I can put it through a HDLC deframer and then kick it out actually over a TCP link. So already I'm enabling my IP. Already then I can transfer this flow graph from a Raspberry Pi and send it straight to my phone. Or I can have these things go into a database, a server, wherever you want these things to go. Let's try and run this one. Well, this is what it's meant to look like. It's got chopped off at the top there, I don't know why. But it's meant to say TNC FSK decoder display. Okay, so we will again tempt fate a second time. Okay, in this particular case, I'm running another flow graph, and this flow graph is trying to then decode in my case, strand, it's an FSK signal, and then I'm going to connect the back end with a separate Python script, okay, that I've written myself. And obviously what I've got here is I've set the filter width to 6 kilohertz, and really that's no good for an FSK signal. We need to have it much wider, and as soon as you set it to something sensible, as soon as it can start to pick it up, you can then start to then kick out packets. So already we're seeing here the running down, and I have to credit Brian Yeomans for a lot of this work, the signal coming in. And you can see it's delimited with our C noughts that we're all very used to seeing in a HDLC standard. Again, there was extra programming that I did just in a bit of Python to just print that out. Here's a TCP packet and just print it out to a console. Not too tough. The rest of that was manipulating those numbers, understanding and matching those rates and deciding what they should be. 2 out of 3. Okay. I've just got to quietly crash that window. Yep, I've definitely crashed that window. Application not responding. Okay, well we can sort that out. There we go, we're back. So when you've done those sort of things, you can then start to figure out where you want to pipe things all around the place. You can then use these systems to build your own SDR front end, and then again use things like GQRX's AFSK decoders. You can then start to use Direwolf or Multimon to then start kicking out data left, right, and center. And this is sort of the good example of the sort of thing that you can do. You can build your own sort of systems where this is APRS ISS traffic. So again, just having a fairly reasonable sort of antenna front end, you can actually get this signal out. So look, we've got guys from Hungary, guys from Kent, Amsterdam, usual crowd across here. But it again means though that with a bit extra, you can then start to manipulate these bits. If you're a satellite amateur radio guy and you're just sort of building these things, you're going to want to understand and get yourself right in and deep with all those noughts and ones and zeros to understand how they all work. So the last thing that I wanted to show you, how am I doing for time? Fine. Is the next one, which is then how we would do perhaps some further analysis. So we've seen kind of again using a wave source file. I can throttle it just to make sure it's definitely coming out at a certain rate, link that up with an audio sync. And then I can have this go through another special block called a Hilbert taps block. And a Hilbert transform is essentially how we can move from the time domain into a circular phase domain that isn't necessarily the same thing as an I and Q phase domain. It essentially produces a discrete convolved output, which is if you give it a function or some sort of signal, will then transform it into the 1 over omega t of this signal. So we're always trying to then rotate it in phase space. Okay? But to do that then gives you a complex output, and then just remember to convert it back into something that you can then use as a float, pass through some filters, recover your clock, binary slice it, pack it up, and then kick it out again through something else. You can start to see that you're just connecting these blocks up. But the Hilbert transform does something ever so slightly special, especially when you want to then analyze your signals and your noughts and ones, which is then, oh, it's still been cut off. I do apologize about that. Which is when you've taken this signal, essentially we'll do a phase shift for negative frequencies and push it around by pi over 2. So if you've got something that's sitting on one of these axes, it's going to want to kind of push it around on this signal. And what that actually means is that sharp edges can turn into frequency component ones and look more like sine waves, but strict edges can then give you quite sharp spikes. And we also use these things as actually quite crude filters to understand and remove oscillations and noise in given systems. And if you do that, that means it's kind of a filter too, and it means then that we're pretty good at detecting differing frequencies, which is also pretty good at FSK and AFSK. So again, finding what these DSP blocks actually do and what they will look like. And what you can do is you can then transform a wave, a baseband wave, out into noughts and ones. You can then slice it and measure it to give you actual noughts and ones out. And what I'll do now is I will tempt fate once again through time and space to understand and actually give us the output we want from my final demonstration. So I'm going to run Gnuradio Companion again. That will load. Excellent. And then I can hit play. I've already got my flow graph. And you can kind of see what I'm doing there is I'm replaying just a wave file over and over again in that flow graph. What I can do is there's a setting that's just here which says repeat equals yes. So obviously if that wasn't there, it would just be a very, very tiny wave and just go blub, and then that'll be it. And we're converting then our audio wave. We're then trying to measure it using a Hilbert transform to know when the changes are in our system. And if I scroll down a bit further, you can see our noughts and ones, and just a bit further again, I then chucked it out as ASCII at the bottom here. Okay, all using the tags and all the tools that are in Gnuradio with zero programming. This one is just dragging and dropping blocks. And it means, though, that you can then start to really play around with the rest of your system. You've then got something that you can then pick out all of these different waveforms about. We're not just talking about RF anymore. People have used that, they've looked at SDR sharp, they've looked at GQRX, but the next step is to go, okay, let's vary that, let's actually sample it, actually get something out of a system and filter it effectively to get something through. And some of the things that you can do can be fairly complex. This is one that I've done that I haven't talked about, which is then about Bpsk and Bpsk decoding. In this case, I've got a signal that I'm looking at. I can then pick it out of a waterfall plot. I can tune it and create my own little menus. I can then look at a filtered signal, what it looks like, and just start to build up your own GUI of what it needs to be. This is my GUD, Grand Unifying Gnuradio one for Bpsk. So you can actually look at the filtered signal itself when it comes in, when it actually blips up like that. You can then fine-tune what the center frequency needs to be. All of these different pieces. And the blocks that perhaps I haven't shown you, okay, which is where the kind of custom, what we call out-of-tree sections are the, how do you get that automatically to detect the peak? How do you get that to automatically understand how wide that signal needs to be for a certain signal-to-noise ratio? All of those things are possible. You do, though, have to investigate them and program them. My current ones, there you go, nice constellation plot there. So this is, in fact, QB50P2. So you can then view real-time your constellation plot. You can view real-time your waterfall. You can real-time even your audio output. And then that is just the actual AX25 packet frame. Unfortunately, I haven't kicked it out on a menu properly because, shockingly, I've got other things to do. But eventually that will come in some form or another, and I'll upload it to GitHub or some other repository. But this can kind of give you an idea, and there's a couple of other options there. That's where I've kind of killed the video, about the CCSDS, forward error correction, and other options that you might want to do. And this is the sort of thing that can really give you an exploration and a bit of power back behind what these tools can do. What you've got is you've got magic blocks, you know, that is doing something wonderful in here, and then you're plugging it into a USB section, and it does stuff. You load that program, you load it in Windows, and it works. And you can hear voice and you can hear audio. And kind of the thing that I want you to take away from that is actually you can do all that yourself. Hopefully, a lot of things that we've talked about, you're familiar with the terminology, but there's just an extra little bit of computer science just added onto the end of it to then start to think about data types and manipulating your bits. So instead of you going, oh, okay, I need a virtual audio cable, and I need to kind of plug that thing back around into here, you don't need to do any of that. You can write these flow graphs yourself. You know what you're looking for. You can then understand what it is you're searching for. If you need to, I can then perhaps help out by giving you some waves where I go, okay, in that little WAV file there, there's definitely a Bpsk 1K2. In that file there, there's definitely something else, FSK 9600. There's ones in here that I've got for Firebird, which is a 19K2 one. And there's excellent, again, repositories online for LilacSat, which is, again, Bpsk. But the ones that I'm interested in and looking at now is things like HORU4. So QPSK signals. OK, let's just keep broadening it out and getting decent reference signals into your system. Hopefully, that is what Graham was looking for.
Perfect.
And hopefully that's been at least something that gives you an idea of what Gnuradio can do.
Yeah, fantastic, Chris. Thank you. Time for a couple of questions. One right at the back.
Sorry.
You've said this is all based on C++.
Uh-huh.
Yeah, why haven't you got the semicolon on the end of the statement?
It was part of an if statement. So if you wanted to continue, then.
When I was trying to receive the 4M mission, which I did what you recommend we don't do, which is sort of add on bits of software like WSJT and all the rest of it, I didn't succeed in receiving 4M. Uh-huh. If I had written a system in Gnuradio in which, because I know what the modulation is, I could have looked for it, does that give me something that I can call processing gain? And if so, how much?
I wouldn't. So when I would think as a gain, okay, I wouldn't say that you're buying back. So this is a definition of terms here where we're actually jumping to quite distinct boundaries. A processor gain would be a performance improvement of some respects. Now, if I measure that in dBs, that already means that I'm probably thinking in slightly differently to what I would expect if I'm thinking about my iPhone processor or a Raspberry Pi processor. So with a processor, I'm thinking MIPS, clock cycles, amount of floating point operations that I can perform. Whereas if I'm thinking in dBs, I'm thinking, okay, what am I trading off here for a given link budget? Okay, I'm thinking I'm trading off data rates with gains and losses in my system. And again, whether or not you've then got some sort of rate scheme and modulation scheme that allows you to then add forward error correction along the same lines. So as soon as you start adding forward error correction, you're buying back dBs. That would be a gain of sorts, but I still wouldn't call that processor gain. Now, kind of going back to your other question about if you had kind of recordings and you did this in Gnuradio, well, this is exactly kind of what people have done to sort of revive back some of the older spacecraft. And they've used Gnuradio blocks because they know what they're looking for, they know what they're searching for. It just depends on your front end. In my case, obviously, I've just got a regular sort of car antenna here, but I'm actually using this SDR. It's got a temperature-controlled oscillator, and has got an EM shield around it, and it's got a couple of component changes inside that one because I'm actually looking for something slightly different in my work. But if you have a decent IQ recording of these things, and there's clearly a signal there that you can put actually quite regularly, whether it's SDR sharp or whatever, and actually you can see a nice big signal down there, well then you've got something to play with. And having something to play with is the first step of that. When you've got that recording, like I said, you can go back over that to your heart's content, which is what I'd recommend you to until you decide to hit your head against the floor, multiple times usually, or you decide to like kind of reach out into the rest of the internet just to see what other people have done. But there's people around this room that I'm absolutely sure be able to help each other, and that's kind of what I've learnt going through this process too.
Okay, last question.
What sort of processing power do you need to run this? I assume it depends on the data rates you're getting through, but
yeah.
Just some examples.
Okay, so the biggest thing that I've worked on is 56 mega samples per second. So you're looking, well, best hundreds of megabits per second, and I use an FPGA for that. And so at those particular FPGAs, then I'm doing most of these blocks that you would see in these kind of other systems. Like these, I would be putting these into raw VHDL, okay, because that's the performance that I need. If you're looking at just this one, which does 2 megasamples per second, a Raspberry Pi 2 can do it, but as soon as you start adding GUIs, that's kind of where things kind of fall over. Like most computing problems that you have, as soon as you start putting printfs everywhere and outputting to the user, it slows things down. It reduces your useful cycle count. But these sort of programs here, Raspberry Pi 3 would do it. Pretty much every laptop would do it. I have an old laptop that I use as just a Linux one, just for demoing bits and bobs, because it doesn't need that a lot. And it's provided, I mean, if you wanted to, you can decimate even further. So even though you're bringing it in at 2 meg, and you're looking for a 1K2 signal, or if it's a pager, even less, then actually you can just decimate it right the way down, or even just not sample as hard. So I can double click on a block and go, yeah, actually I don't need 2 megasamples. I only want 50K, or pick something though that is typically falls on a 32-bit boundary that's nice for a processor to utilize. So, yeah.
May I add one extra bit in there on that?
Sure.
Everybody thinks you can reduce it down. Everybody thinks you can reduce it down and keep decimating and keep decimating. If you are going to use any of the GUI sinks that give you a waterfall and all the rest of it, don't go too low, because they can't handle it.
Oh, yeah.
I've discovered
Yeah.
the hard way.
Yeah, I mean, you're going to be probably oversampling by, hundreds of times usually than you actually need to. What's really, really good is that if you go down actually to about 8,
That's when it starts to get.
it usually does start to fall over. Thank you very much.
Okay, thank you very much, Chris. I've certainly learned a lot. and I'm sure everybody else has as well. So thank you very much indeed for that introduction, at least for me, an introduction to GNU Radio.